So kind of wrapping up, thinking about hybrid states. The biggest thing to think about when you're thinking about hybridization states is to think about what type of bonds that atom has. Really, how many pi bonds does it have? That's the key, right? So if you look at this carbon right here, right, this carbon right here, what kind of bonds does that carbon have? It has 4 bonds, right? Octet rule, 4 bonds. It has a sigma, a pi, and a pi bond. Now if I were to label this carbon 1 and this carbon 2, so this would be C1, what kind of bonds does carbon 2 have? What kind of bonds does carbon 2 have? It has 3 sigma, very good, and 1 pi. Notice it's always 4, right? It's always usually going to be 4. You have 4 atomic orbitals always, 4 hybrid orbitals. Now, what's the hybridization state of C1? How many pi bonds does it have? 2. Therefore, it has to have how many of these guys? Show me your p orbitals. See them? Got your p orbitals out, ready to make some pi bonds, right? If you have a pi bond, you must have a p orbital, right? So if you have 2 pi bonds, how many p orbitals must you have? 2. So I'd have a p and a p. The hybridization state then is sp, and the orbitals making the sigma bonds then are sp orbitals. So make sure you distinguish between hybridization state, hybrid orbitals, and the bonds they make. All right, let's do this next one. C2, what's the hybridization state of C2? How many pi bonds does it have?
1 pi bond.
1 pi bond. So it must have,
sp2.
so it's sp2, so it has 1 p orbital, and everything else nice. Okay. C1 and C2 are bonded to each other, correct? What bonds do C1 and C2 have with each other? They have a sigma bond and a pi bond. Which hybrid orbitals are making the pi bond? P orbitals. It's only p, right? Only p orbitals, right? So these two must be making a pi. They must be making a pi bond, right? Using that 1 p orbital here for that. What hybrid orbitals are making the sigma bond between C1 and C2?
sp and then sp2.
sp and then sp2. So pi bonds are only made from what? P orbitals. But sigma bonds can be made from sp3 and sp3, sp2 and sp2, sp2 and sp3, sp and sp, sp3 sp, sp2 sp, right? Sigma bonds can be made with all those different types of hybrid orbitals. But pi bonds are only made with
p orbitals.
p orbitals. Thank you, Randy. Yes. So let's take a look at some formal charges. So we're assuming there's a full octet in all of these, or everything's drawn in. Any formal charges on this first one? That's acetylide. Should there be a formal charge anywhere? So this carbon would have a negative charge. Excellent. What about HF? H2F. Right, so this fluorine has a plus charge. Too many bonds. It only wants 1. Too many bonds. What about that phosphorus? Where's phosphorus at the periodic table? So the phosphorus should have a negative charge. It wants to have 3 bonds. It has 2, but it has a full octet. Negative charge. How about this oxygen? How many bonds does oxygen want to have? 2. How many bonds does it have? 3? That's too many. Does it have a full octet? Yes. The oxygen should have a plus charge. That's right. So question, sp3 hybridization state, sp hybridization state. What hybrid orbitals are making this sigma bond? Right? Well, each hybridization state only makes sigma bonds with one type of hybrid orbitals. If you're sp3, what are your hybrid orbitals? You have sp3, 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 and sp3. And they all make sigma bonds. If you're sp hybridized, you have two p orbitals, right? Because you're making two pi bonds. Your other hybrid orbitals are s and p, are sp orbitals. And what bonds do they make? You only know two types of bonds, the sigma bonds. So by knowing the hybridization states, you know which hybrid orbitals are making which bonds. So which bonds are making it there? sp3 hybrid orbital and an sp hybrid orbital are making that sigma bond right here. So we're going to resonance now. What are the 4 rules? Rule number 1, and these are in your book.
Octet rule.
Say it again.
Is it the octet rule?
You always, not necessarily. Nope, not the octet rule for this one. Even simpler, even simpler. We're thinking, and this is in this part of the book, I'm thinking positions don't change. Atoms can't move. That's what that basically means. The atoms don't move. You're only moving pi bonds, pi electrons, and lone pair electrons. So that's this number 2. Atoms don't move. Only thing that moves are non-bonding electrons and pi bond electrons. Those are the only 2 things that move. Atoms don't move, electrons move in resonance structures. Sigma bonds don't break. Sigma bonds don't break. So you have to have pi electrons, which means you have to have a p orbital. So which hybridization state has nothing to do with resonance structures usually?
SP3.
sp3, because it has no p orbitals. So it can't have, right? It only has sigma bonds. So sp3 atoms have nothing to do with resonance. Good.
What about a triple bond?
Triple bond's sp hybridized, so it can do resonance, right? It has p orbitals. And we'll show an example of that. Good question. Number 4, you must balance your charge. You must balance your charge. Balance your charge. If you make a resonance structure that has a negative charge, if you start out with a resonance structure that has no charge, and you make a new resonance structure that has a negative charge, you also need to have a positive charge somewhere. Balance your charge. So resonance is very stabilizing. So even though there's a negative charge here, right? This is a carbanion. What hybridization state is it choosing to be? These atoms are making a choice about their hybridization state to get as low in energy as possible. And I just told you resonance is really a stabilizing thing. So if you can do resonance, what are you going to do? You're going to do resonance. So even though this is a carbanion, and if you didn't see this, if this was by itself, maybe if it looked like this, could this do resonance? No. To do resonance, you need to be next to other pi bonds. There's no other pi bonds here. So what's the hybridization state of this going to be? It's going to be sp3. But in this case, because it can do resonance, it's going to choose to be sp2 and have a p orbital so it can spread those electrons around. Now, one thing you'll notice, where do arrows always start? Arrows always start at electron density. They never start at plus charges. So if you have a negative charge, start your arrows there and move the electrons. Also, you should number your carbons. That way you don't lose any, and you're keeping track of what bonds are being formed, what bonds are being broken. Right? So loop them around, break the pi bond, make a new pi bond. That's a resonance structure with a carbanion. What if you have a carbocation resonance structure? We already know carbocations are going to be what hybridization state? sp2 to have an empty p orbital. So now we're going to move those electrons right towards the plus charge. You move electrons towards electron deficiency. You start at electrons and move them towards electron deficiency, and then you got your resonance structure here. We're not even going to worry about single-headed arrows right now. We're worrying about double-headed arrows, right? Resonance structure is that way. What is the hybridization state of a carbanion or an element with lone pairs when they are next to a pi bond? So if you're a carbanion, have a negative charge, a lone pair of carbon, or you're an element with a lone pair, and you're next to a pi bond, what hybridization state must you be if you want to do resonance? Or at least which one can't you be?
You can't be sp3.
You cannot be sp3. And why is that? Because sp3 has no
resonance.
sp3 has no what, Liam?
Pi bond, so it can't do resonance.
sp3 has no p orbitals, which also means it has no pi bonds, right? So it can't do resonance. But atoms will make that choice. If you're a carbanion or if you're a lone pair, you will choose, if you are next to a pi bond, to be sp2 hybridized. So then you can have a p orbital, and that p orbital then can be used for resonance. Let's look at some examples. So these are from the book, all right? Actually, you know what? Let's do some clicker questions. Let's back up and do some clicker questions. Let's take about 10 minutes. Any questions as I'm going along here? I like to think this is review, but I know this is always one of the most confusing parts of organic chemistry, but this sets the groundwork, right? If you can understand how bonds and resonance works, those are all reactions are understood. Right? If you understand this, we apply this to every single reaction you'll learn from now on, or have before. All right, so we'll go back to top hat. Start presentation. All right. Start question. Which resonance structure results from the arrow pushing pattern below? Everybody can see that? Or you can see it on your top hat too, hopefully. So the arrow's shown. What's the right answer there? Couple more answers. Three more. I'm going to stop it. 3, 2. Close it. Let's see how we did. I think we did pretty well. Yeah. You see it? So which one is it? We're moving electrons from the nitrogen towards the oxygen. So we're making a new pi bond between the nitrogen and the carbon. We're breaking the pi bond between the carbon and the oxygen. Was there any charge in the starting material? No. So there can't be any charge in the product. So the answer is D. Right? Who's giving up electrons? Who's getting more bond? Right? This comes back to, again, we talked about formal charges. Right? This is always a good check for yourself. Like, wait, nitrogen also has 4 bonds. That's not right. Nitrogen wants 3 bonds. It has to have a plus charge. Well, if it has a plus charge, something else also has a negative charge. Right? Take those ideas and the things you know from before, that chemical sense, and apply it here. Questions on that one? What's the hybridization state of that nitrogen? What hybridization state is that nitrogen?
sp2.
sp2. Excellent. Now, how'd you know that?
There's a pi bond.
The lone pair, right? The nitrogen with a lone pair, which is one of our rules on non-bonding electrons, a nitrogen with a lone pair is next to what? Is next to a pi bond. That means it can do resonance. If you can do resonance, will you do resonance? Every time. It's not even about charges. It doesn't matter. Right? It'll do resonance. Actually, this one's cool. Anybody recognize this bond? What kind of bond is this? This is really why we're standing here. This is like the foundation of life right here. No big deal. Anybody know what kind of bond that is? It's an amide bond. What are amides made up of? Or what is made up of amide bonds? Proteins, peptides, right? Those are really strong bonds. Why is a carbon-nitrogen, that bond, really strong? Because of this resonance structure. Or that nitrogen-carbon bond has some double bond character. That makes that a very, very unreactive bond. And that's why we're alive. Right? Chemistry for the win. Versus an ester, right? Those bonds are easier to break, a carbon-oxygen bond. Because it's more reactive, it's a more polar bond. Anyway, good. Okay, let's go back. And finish this. Are you back to seeing the resonance recognition? So these are all just things to kind of look for. You'll start to see these patterns. I'm not saying, I would never ask you, hey, what's resonance recognition number 2? Like, no, that's not how. It just helps you see there's 5 of them. And they're all kind of different. So like this one is very similar to the one we just did, right? This is an ester, but this is an oxygen that's neutral, but it has a lone pair next to a pi bond, and it can do resonance. Here's the carbocation version, right? Well, notice where the electron's moving. They're moving towards the plus charge. Number those elements. Again, negative charges moving towards the plus charges. Electrons moving towards the plus charge. Here's a good one. Send me in the tech chat. Which one's the more stable resonance structure, A or B? Which one's the major resonance structure? A lot of people have questions about major and minor resonance structures, right? I saw that in our feedback. Which one's the major, A or B? Which one's the major? A or B, A or B, A or B, A or B. Nice. Nice. Yeah, keep it coming. It's good. A or B, which one's the major one? Everybody turn their sound on. You've earned this. If you're going to mess up, you're going to mess up epically. What's the rule? The octet rule. The octet rule. The octet rule. The octet rule. Which one of these doesn't follow the octet rule? A or B? A. Who cares? Right? Lewis dot structures lie to us. Look at B.
Yes.
Look at B. Look at B. Everybody has a full octet. Who cares octet has a plus charge? Who cares? Everybody has a full octet. This is the major resonance structure. The octet rule. The rule to rule them all. Now, why do we do resonance structures, though? So somebody would be like, oh, for the love of God. Like, why are we doing this then? This is confusing. Because why we're thinking like chemists now, right? We're thinking like organic chemists. If I see this, I know, right? Is the oxygen really electron deficient? Not really, no. This resonance structure tells me actually it's this carbon that's electrophilic, not this oxygen. So resonance structures help us understand how things react. But the octet rule is the most important rule, right? So again, this has been inundated in your head. Charges are bad, right? You've been like told this. Charges are bad. Charges are bad. Octet rule is more important. Resonance and octet rule. Those are the two things you learned today, hopefully. Reinforced. All right? All this stuff's available